Hello, everybody, and welcome back to Markov processes. A new homework is coming out today. We haven't had one of those for quite a while. And it'll be mostly on queuing and certainly on the stuff since the exam and the Monday right before the exam. We are going to continue talking about MM1 processes, or an MM1 process, which is a queue with one server. And we're not going to be talking about this all day. We've talked about it quite a bit already, but we were in the middle of a computation, and that was the computation for the waiting time. I'm not sure if I asked for the distribution or the expected waiting time, but it was the waiting time of a typical customer in the system. So we have the, oops, that's not going to work. Okay, so we're talking about an MM1, and the two M's stand for memory lists, which implies exponential distributions. So the queue is a server that has service times that are exponential with rate mu, and people coming in according to a Poisson process with rate lambda, which means the inter-arrival times are exponential with rate lambda. They get served and they leave. And we have found the stationary distribution for the number of customers in the system at time t. So number customers in the system at time t, and this includes the person in service. So not just in line, but a lot of things you might be reading out there if you're Googling stuff, it might say they might talk about the number of customers in the queue and really be talking about this, which is technically correct because this whole thing is a queue. But of course, some of us understand a line to be a queue. And so are we talking about just the people waiting or everyone in the system? So while I am using this in system all the time to make sure that's emphasized, be careful when you're reading other things. Okay, so we found the stationary distribution. Now this is continuous time, but it's got a discrete state space, and we saw a geometric distribution. We saw the long run probability of there being n people in this system was 1 minus lambda over mu to the n, and that this holds for n equals 0, 1, 2 on up, which is a nice little geometric distribution, the one starting from 0. Okay, so we talked about a few things like what is the expected number of people in line and stuff, and we were in the middle of a computation, which was, I'm not sure, again, if I asked you the distribution or the expectation, but let's go over the expectation because we're going to need to find the distribution. So what is the expected waiting time? So not service time. We're going to talk about that next, and that is called the sojourn time, which is the waiting time plus the service time. So that's the total time a typical customer spends there. This is waiting time plus service time. We just want the time they spend waiting in line. So this is the expected waiting time of a typical customer. That's TYP for typical customer in equilibrium. That's EQ for equilibrium. So we were looking at, well, we gave this a name last time, I think. I think we called it W. So I'm going to let W be that waiting time of a typical customer in equilibrium, the exact thing in here. So I want the expected value of W. So we last time were saying that this is a mixed random variable, that it has a discrete side to it, but it's mostly, whatever that means. That doesn't mean anything. I was going to say mostly continuous. So a person can come up to this system and there's no one there, no one in service, no one in line. They go directly into service and they have 0 wait. So it is possible to have W equals 0 with some positive probability. But once the wait is greater than 0, then it becomes a continuous random variable. And the probability of, for example, having a waiting time of 1.2923881 minutes is 0. And it's 0 for any particular fixed given value. And we had just started that second computation. So let me just remind you, because it's only a line, The probability that the wait time is 0 is the probability that the system is empty when the person arrives. And here I'm kind of hiding some pasta, which I've yet to prove, because is the arrival of a person, are they seeing the queue in stationarity? And I claim they are by this pasta property. So, this is a really specific kind of random time we're looking at the queue. It's not just random in the sense that people on the street say, you just picked a random time, meaning no rhyme or reason. It is a random variable that has to do with a person arriving. So if you don't believe pasta, which I have yet to prove, then maybe you don't believe this line, because the pi 0 is the probability the system is empty at any given time. And whether or not that holds for this particular kind of time when someone's approaching, we still have to prove that. But let's say we prove that. This is our pi 0. And that was 1 minus lambda over mu. And remember, for this whole system, we did need lambda to be less than mu, or the thing would be unstable, and we wouldn't get a nice we wouldn't get a nice stationary distribution. The line would blow up, meaning an infinite number of customers. It would just get bigger and bigger, and it wouldn't come to an equilibrium with a certain distribution on the non-negative integers. So with probability, that's my WP, lambda over mu, what can we say? Well, the waiting time is greater than 0. So, and let's look at the PDF there. So assuming the wait time is greater than 0, what is the PDF, the continuous PDF, or the PDF for that continuous variable? What is the probability density function for W? I am going to write in quotes what I think I'm going for, because it's not exactly what I'm going for. So I'm looking for the PDF for W in this case. I think I would probably want to try to write this as the PDF for W, given that W is greater than 0. But bear with me until the end. So this is us going for it in a sort of a conditional case. Okay, so that's why I put it in quotes. So we know we're in the case where W is greater than 0, and that happens if and only if there's at least one customer in the system. So we can condition on that number of customers, and this will be the sum, and this does imply that we are in this situation where W is greater than 0. So we have to have 1 or 2 or more customers, and we want the PDF for W given the number of customers, and then the probability that there's n customers, which is our pi sub n. So this probability is pi sub n, and this is the gamma distribution with parameters n and mu. We talked about this last time, but if the person comes up when there's n people in the system, they have to wait through n IID exponential rate mu service times, which adds up to a gamma amount of time. And also we talked about the fact that when that person arrives, someone has already started their service, but the remainder of service for that person by lack of memory is still exponential with rate mu. So that's why we're not looking at n-1 IID exponentials and then a remainder time. We can just wrap it all up in n IID rate mu exponentials. I know the PDF for this, so let's plug it in. Okay, so it looks like I'm using the variable little w here. The gamma PDF is 1 over the gamma function of n, mu to the n, w to the n-1, e to the minus mu w. And then I've got the pi n on the end, and that is 1 minus, so here's where this breaks apart, 1 minus lambda over mu to the n. Right. We got to do a sum. So let's get rid of all the stuff that does not involve n. For example, this e and this guy, and looks like everything else involves n. So I'm going to pull those two things I just circled out. This is e to the minus mu w, 1 minus lambda over mu. And then the rest of the stuff is in, you know what, before I do that, let's make this a little simpler. I have a mu to the n, and I have a mu to the n in the denominator. So those are going to cancel. And what I have left is the sum from 1 to infinity. I'm going to use the fact that gamma of n is n minus 1 factorial. So I've got that in the denominator. And what's left up here, I've got a w to the n minus 1 and a lambda to the n. So let's get all those exponents the same. Let's pull a single lambda outside. And then we have the sum from 1 to infinity of lambda w, or w lambda, to the n minus 1 over n minus 1 factorial, which of course we can re-index to start from 0. Now you don't have to do this if you know what this sum is, but if you are really leaning into a few Taylor series that you've memorized, then maybe you do want to do this. And that is, this is the sum from 0 to infinity of lambda w to the n over n factorial, which is e to the positive lambda w. So let's bring this all together. The last part of this is going to be e to the negative mu minus lambda to the w. And so what I want to see out here is lambda over mu. Yeah, okay, so I can write this as lambda over mu, mu minus lambda. So, right, yeah, that's right. That's equal to the line above. And the reason I kind of knew what I was going for is because I saw this part, and it looks like an exponential with rate mu minus lambda. So right here, but not the whole thing, is the PDF of an exponential with rate mu minus lambda, which by the way is okay and safe here. The rate parameter always needs to be positive, but we are in the regime where lambda is less than mu. Otherwise, we never could have plugged in the stationary distribution up here. We wouldn't have one. So because we're in the regime where lambda is less than mu, then this rate mu minus lambda is positive, which is something that is necessary for an exponential distribution. Now, this is a PDF, and that integrates to 1. But what about this lambda over mu in the front? This is not going to integrate to 1 if you integrate as w goes from strictly greater than 0 to infinity. You're going to get 1 for the PDF part, and you're going to get lambda over mu. So what we're really seeing here is, so to sum it up, because I think it's kind of hard to, I think it's easier to talk about these mixed random variables with a couple of bullet points like this. So we can say that W equals 0, W being the waiting time, with probability 1 minus lambda over mu. And then with probability lambda over mu, W follows an exponential distribution with rate mu minus lambda. So if you really wanted to go give notation for the original thing where I put the PDF in quotes, we did not find, if you think about how this is the probability that W is greater than 0, and the fact that the conditional PDF for W, given W is greater than 0, is going to be the joint PDF. This is hard to write down, right? Because W being greater than 0 has a positive probability, and yet we have a continuous random variable here. But continuing, we'd have like the probability that W is greater than 0. And in fact, this weird numerator that I don't even have a good notation for is really what we just found. It's the PDF for W, it's not conditional, but we are only plugging in W's greater than 0. So it's also not a joint PDF, you know, even though we have two things in the subscript. It's just weird. So I'm just going to write it like this. It's this mixed random variable that takes on one value with some probability, and then with another probability, it takes on other values. And if you wanted to simulate this, you could grab a uniform and compare it to this. And if it's less than that, then you can carry off an event that happens with that probability. So you can set your W equal to 0. And if your uniform was not less than this, then you can go simulate from an exponential with this rate. And you don't have to worry about this. That's just 1 minus this. That's already taken care of by the kind of coin flip you're doing at the beginning, the unfair coin that says 0 or not 0. So what is the expected waiting time? Well, I don't really think we need to go too far into mixed random variables, but the expected waiting time for a mixed random variable is what you would think it is. It takes on a value, maybe 2 in general, with some positive probability. So it's going to be starting out like a discrete expectation. It's going to take the value 0 times the probability 1 minus lambda over mu, plus the expectation of the continuous part. So plus the PDF we found here. So we've got lambda over mu times the integral from 0 to infinity of w times the PDF, which I just said I don't have good notation for. But really, it's going to be this exponential rate, mu minus lambda PDF. And we know the mean of the exponential. So we're going to end up getting lambda over mu times, which is here, times the mean of the exponential, which is 1 over mu minus lambda. Yeah, so we're done. But without going too deep into it, that's how you compute the expectation for a kind of mixed random variable. You multiply and add the points that you can, and then you do a continuous kind of expectation. And this is all formalized through something known as a Riemann-Stieltjes integral, where you define all of your probability in terms of CDFs. And CDFs, where you have like positive probability points, have jumps, and you have to define what an integral means over those jumps. And it's pretty natural, but it's a whole different thing. Okay. A really quick computation before we go to the next Q. So we're in, let's say, an MM1. The default parameters are always lambda and mu. And what is the expected sojourn time? So I defined sojourn time already to be a person's total time in the system, their waiting time plus their service time. And that's all it is. This is the expected waiting time plus, now I need notation. Do we call the sojourn time S, or do we call the service time S? And is that S going to be confused with the S sub n's that we've been talking about? Yes, and yes. So this is a service time in this case. And this is, of course, the waiting time. And we know this stuff. We just computed that the first expectation is lambda over mu, mu minus lambda. And the expected service time is 1 over mu because the service time is exponential with rate mu. Okay, a new Q. This is my least favorite one, and that is the mmsq. And I think it will be your least favorite too. It's just kind of hairy, so that is a lowercase s. And look, another s to confuse us. But s is definitely the letter of choice, not that you have to use that. And what's going on here is we have a Poisson input stream with some rate lambda. And we have S servers, where S is greater than or equal to 1. We have that all servers use or have IID exponential rate mu service times. It is a building block. I imagine you would like different servers to have different service times. So that is another queuing model, but it doesn't have, it's not what the MMS is defined to be. So they all have the same IID exponential rate mu service times. And the routing is this. I am too lazy to write this, but I'm going to describe it. So people come into the system according to a Poisson process with rate lambda, and we have S servers, and they each have rate mu, And the person just picks an empty server if one is empty. But if they're all at work, then they start forming a single line. And then the first person to leave, the next person in line will go to that server. Kind of important, but I'm too lazy to write all that. So it's not like we're lining up individually at different servers. That's just a different model, which we'll talk about. Okay, let's find the stationary distribution. I mean, not an exclamation point, although it is exciting, but a question mark. It's another birth and death process. What are the birth and death rates? When we know them, we have a formula for our pi n involving the lambda i's and the mu i's. So this is a birth and death process. And the birth rates are constant. It's a constant lambda. When there's currently I people in the system, the rate of the next arrival is still just lambda. And so this holds for I equals 0, 1, 2, etc. Now for the death rates, if there's no one in the system, then no one is dying. The rate of death is 0. If there is one person in the system, then there's actually no one lined up and only one server busy. And so the time of departure for that person is exponential with rate mu. So the rate of departure is mu. If there are two people in the system, then assuming that the number of servers is greater than one, there's still no one waiting in the line. There's just two servers working. And the next departure is the minimum of those two service times. And those are IID exponential with rate mu. So the minimum of those two service times is exponential with rate 2 mu. Same thing for mu3, 3 servers, they're all racing. And the assuming 3 is less than or equal to S. So S is a predefined parameter here. 3 servers are going to be racing, each exponential with rate mu. And so this will hold all the way up to, if there's currently little s people in the system, then that picture is just, there's someone in every, at every server, and there's no one out here. And so we've got S exponential rate mu's all racing, and so we get S mu. And we stay at S mu because if we have like S plus 1 people in the system, now there's someone over here as well, but we still have the next departure when one of these S people is finished. So we have to look at the minimum of S service times. So this departure time is still, or departure rate is still S times mu. And it stays that way. If we go up to S plus 2, it's still S times mu, right? But people aren't departing any faster. They're just piling up in the line. And so we can say mu sub I is S mu for all I equals S plus 1 on up. Okay, sorry, just catching up on my chat. So we have a formula for the stationary distribution. Remember, it looked like this. Pi of n is lambda 0, lambda 1, up through lambda n minus 1 over mu 1, mu 2, up through mu n times pi 0. And this is going to be awful. So let's suppose that n is less than or equal to s. In other words, n is 0 or 1 or 2 up through s. Then we have in this thing, we've got a lambda, lambda, lambda. We've got n lambdas up here. And we've got a 1 mu, a 2 mu, up through an n mu here. Now, if n was greater than s, then we would have a bunch of kind of repeating terms on the end. But right now, and we have pi 0. Right now, I've got lambda over mu all to the n, and I've got a 1 over n factorial times pi 0, which holds only in this case. Stop me if it doesn't make sense. So for s being n what I want for n being s or greater, I realize that I do have some overlap here, but things will be defined so that it comes out to be the same thing. So it's no concern. The pi n is lambda. We're still talking about n people, so we're still talking about n lambdas, but we have a 1 mu and a 2 mu, and we get up to s mu, and then we continue with the s mu's. And this is going to be n minus s terms there, n minus s times a pi 0. So this, in this case, for these n, we get lambda to the n over mu to the n. So the lambda over mu to the n still holds because I have a total of n terms in that denominator, or n. Yeah, I don't know, aren't terms just for things you add? Got a total of n factors. You know what I mean. So overall, I've got lambda over mu to the n. And then in the denominator, this part gives me 1 over s factorial. S is a fixed given number. And then I get, so I've already counted these mu's for a total of n of them over here, but I do get s to the n minus s. Right, so the final thing we have to do to give the formula is to solve for pi 0, which we're not going to be able to do explicitly. So the answer here is, I'll give you an expression for it, but we're not going to be able to get a closed form expression. Pi n is lambda over mu to the n 1 over n factorial times pi 0. And in this other case, it is lambda over mu to the n 1 over s factorial, s to the n minus s, pi 0. This is for s equals 0 up to n. And this is for s equals n on up. And if you plug in s equals n, you'll see that they match. So it's okay that I've overlapped here. And then you just have to say where pi 0 is. So you want to sum up as n goes from 0 to, I'm going to say s minus 1, because I don't want to sum up that overlapping term twice. So I have to pick which sum I'm going to put it in. But I get lambda over mu to the n 1 over n factorial. And then the rest of the sum, n equals s to infinity, lambda over mu to the n 1 over s factorial, s to the n minus s. And that whole thing doesn't fit, but there should be an inverse on this whole box. So let me move it. Okay, so inverse. Yes, no, yes, yes, thank you. The s to the n minus s comes from the remaining n minus s terms over here. So that should be in the denominator. Thank you so much. So this is 1 over up here, and 1 over in here, and 1 over in here. Questions? Does anyone vote for this being their favorite Q out of the 2 we have so far? It's really yucky. But if you put in s equals 1, then you get the MM1, so all is right with the world. I'll tell you what my favorite Q is. It's the next one. Yeah. It's MM1 versus MMS. Yeah, S being the number of servers. So the next one is an MM infinity, which you kind of know what this means. It's an MMS, but S is infinity. So an MM infinity, it just is the same sort of setup, but we have an infinite number of servers. And this is used all the time to model things where you will have a finite number of servers. that where you want that. So suppose, I don't know, suppose it is the early 1900s. Did they have switchboards then? Suppose CU in the remodeling is going to be reinstalling all of the landlines in the buildings, but not everyone uses a landline anymore. Do they need to put it in the building anyway? Should every professor and staff and student have this? I don't know. We're trying to figure out the number of landlines to install so that, so I'm assuming that only a finite number of calls can be made at the same time. So that's why I'm doing this old fashioned kind of, there's someone with a switchboard plugging us in. And if you want to know how many lines to install so that you can handle all of the calls 99.9% of the time, then you can use an infinity queue. You can solve for your pi n's, and then you can sum as n goes from 0 up to an n that we need to solve for, pi n, and set that equal to 0.9999. So most of the time, at least in my experience, an infinity is really a precursor to a finite number of servers where you're trying to figure out the finite number of servers so that you can serve everyone with a certain specified probability. Does that make sense? So I didn't write that down. I'm so lazy. But I'll write that part in the notes. So this is exactly what you think it is. People come in according to a Poisson process with rate lambda. There is an infinite number of servers, goes on forever. They all have service rates with rate mu. People go to a server if there's one empty, and there's always one empty. So no actual line forms back here. There's no one here. And the birth rates, the lambda I, the birth rates are constant. They're lambda. That's the rate of people coming into the system. So this is for all I. The death rate, if there's 0 in the system, is 0. If there's 1 in the system, it's just that one person's service time. If there's 2 in the system, it's a race between 2 exponentials. And we just keep going. So mu sub n is n times mu, which is a nice formula that actually ends up holding even in the case of 0. So I'll say n equals, well, if I want to make it look like what we're used to seeing, I'll call it mu sub I. So the death rates, mu sub I, are I times mu, for I equals 0, 1, 2, etc. This is going to be nice. So the stationary distribution pi n is lambda 0 through lambda n minus 1. These are all the same. Over mu 1 through mu n, those are all the same, times pi 0. And we simply get lambda over mu to the n pi 0 for n equals, this formula, we talked about this last time, this formula happens to hold if n equals 0. Because if I plug in a 0 here and a 0 here, oops, and a 0 here, and a 0 here, this goes away and is 1. And so I do get pi 0 equals pi 0. But there are actually some cases where the formula will only hold for n equals 1 on up. But this one, it holds even for 0 customers. And we need to find the pi 0. And we'll do this just like we did in the MM1 case, just like we did in all cases, actually. We're going to sum these up and make sure they sum to 1. So I'm going to take 1 and set that equal to the sum as n goes from 0 to infinity of pi n. When I put in these mu's, I needed to put in I times mu. So 1 times mu, 2 times mu, etc. I'm going to end up with a 1 over n factorial here. Okay, let's sum it up. This is the sum as, so I'm going to sum this up and I'm going to just pull the pi 0 out already because I know that's going to come out. This is the sum from 0 to infinity of lambda over mu to the n over n factorial, which is a Taylor series or Maclaurin series expansion for e to the lambda over mu. So this is pi 0 e to the lambda over mu, which tells me that pi 0, which I get by dividing this over to this side, is e to the negative lambda over mu. And when we put it back to our formula, we had pi n in terms of pi 0. So I'm going to plug it in up here. We now have that pi n is e to the minus lambda over mu. Sorry, my last mu looks like an n. Let me fix that. Lambda over mu to the n over n factorial. A nice Poisson distribution with parameter lambda over mu. So the number of people in the system, including the ones in service, which they all are for the infinity, is a Poisson with parameter lambda over mu. This is not a Poisson process. This is just a Poisson random variable. I really wish I had written down the lead up to this, because I think that's really important. And that is, if you're trying to figure out how many things you need in order to fulfill a certain capacity, and you know, for example, in the telephone example, you know the rate of phone calls coming in and going out, then you could set that up as an infinity, and then again, you could take these pi's and sum up to some value and set that equal to a probability that you'd be comfortable with if you want to say in equilibrium, I will have enough phone lines to cover everyone 99.99% of the time. Let us look. We do have coming up, but we're not going to talk about it today because it's too deep a discussion to do in the last 8 or 9 minutes. We will be talking about not next today, but next class, an MG1Q. And that means we're back to one server. The inter-arrival times are memoryless or exponential, so the arrival process is Poisson. And this G stands for a general service time distribution. You can use your favorite continuous distribution for the servers. And it's really hard to work with these. It's really ugly because we don't have that lack of memory that we keep using. So if you want to know the expected weight of a customer, and before I said if there's n customers, they have to wait through n exponential rate mu service times. That part is going to be a lot harder if we don't have exponentials there, but we'll get there. Okay, so what can I get in today? The departure process for an MM1Q. Why? Why do we care? This is important when you want to start stringing queues together, like in tandem. You know, you go to the first server, and usually you would have something more like this, like you go to the first server and then you're either done or they send you to somewhere else, you know, like customer service or something, but we're not there yet. So just a tandem queue like this. If the input rate here is lambda and the service rate here is mu, what does that mean for the input rate here? So let's find out, because we want to look, the input rate here is the departure rate from here. So I'm going to call that D. Let's suppose there was just a departure, and immediately after we want to look at the time until the next departure. So suppose a customer just, and I mean instantaneous, just left or departed the queue, the system. I'm going to let D be the time to the next departure. I want to know the distribution of D. So let's do it. Let's go for the CDF. Why? Because I can interpret that much better than I can interpret PDFs, because it's a probability. So if we look at the probability that D is less than or equal to T, or maybe you used a little d, or maybe you used an X, but it's time. So I'm going to use a T. I can break this up by conditioning on whether there were any customers left in the system when that last person left. So I claim that this is the probability that D is less than or equal to T, given there were 0 customers left behind by that departing customer, times the probability there's 0 customers left behind by that departing customer, plus the probability that D is less than or equal to T, given there were greater than 0 customers left behind by the departing customer, times the probability greater than 0 customers left behind. I want to say that we know this. I'm assuming this is all assuming we're in equilibrium mode. When a customer leaves and looks back, they do see, I didn't realize how much I would use this today, or I would have proven pasta first thing today. So we'll do it first thing next time. A customer arriving, what they see ahead of them is stationarity. We talked about when a customer was departing, and if they look at the queue just before they depart, it's not the same stationary distribution, because in that case, they'll never see, for example, 0 people in the queue because they're always 1 person. But if the departing person leaves, is not in the queue and looks behind, then they are seeing a distribution which I claim is still the stationary distribution. So once again, we have this question of, can you look at this kind of particular time point and still have stationarity? And I claim you can. And so I'll have to prove that next time. But this is going to be, if in the case that there are 0 customers left behind, the time until the next departure is an arrival time plus a service time. So this is going to be, should probably use an A. It looks like an event. So this is an inter-arrival time, which is exponential rate lambda, and this is a service time. So that's got to be less than or equal to T. And then the probability that there's 0 customers in the system, which I just argued was what the person leaving sees, the steady state probability. This is pi 0, which we know for this MM1Q. That's 1 minus lambda over mu. And then the other term, if there were greater than 0 customers left behind by a departing customer, then the next person goes immediately into service. So the next departure time is just a service time. So this is the probability that the next service time is less than or equal to T times 1 minus pi 0. This is easy. This is the CDF of an exponential with rate mu, because that's the service time distribution. This is lambda over mu for the MM1. This is 1 minus lambda over mu. And this one, I would compute by conditioning on one of these 2 random variables. I would condition probably on S. I think it'll work out nicer. I definitely don't have time, but you know what we're going to see when we get through this? We're going to get 1 minus e to the minus lambda t. We're not going to see any mu. So the inter-departure times are exponential with rate lambda, regardless of what mu is, although we did use these things, which only hold when we have mu greater than lambda. So assuming mu is greater than lambda, the service time is fast enough to get people out so they don't pile up. The departure process looks just like the input process and has nothing to do with mu. And we can show even more than the time. We can show the other properties of a Poisson process, and we will conclude that the departure process of the first server is a Poisson process with rate lambda. So the input to the second server is just like the input we originally had. And we're going to show that the number of people, if we have, so we've got these 2 tandem queues, we've got customers waiting here and customers waiting here. And we're going to maybe look at like the joint probability of the number of customers currently waiting at each station. And we're going to see that these are independent, and they're independent MM1 queues, because the departure process here is just like the arrival process to start a new MM1 queue. So that's super cool and super useful for putting together blocks of queues. So We'll see that next time, as well as pasta that I keep promising. And then I'm out of time, but something really cool. Okay, I'll tell you. We're going to discretize time, but where can you discretize time to get the right distributions and what's going to happen? And next time on Markov processes.